To start off, I'd like to introduce Professor Katherine Richardson, Professor in Biological Oceanography, Globe Institute, and leader of the Sustainability Science Center at the University of Copenhagen. As Professor Richardson will discuss, humankind cannot continue to flourish unless the Earth and its resources are more proactively and productively managed. Professor Richardson will consider how best this can be achieved and review the parameters of the planetary boundaries framework, which identifies science-based limits for human perturbation of the Earth, system processes, and where things stand relative to this. Let us welcome Professor Richardson, who will speak on Planetary Boundaries, a tool to guide management of human-Earth interactions. Welcome.
Okay. Thanks very much, Lori. It's a great pleasure to be here. As Lori says, I am actually trained as a biological oceanographer, and somebody taped that title onto my professorship. But in fact, I've used the last 30 years of my life or so together with a large international team, including, of course, Johan Rockström here from Sweden, to try and study the Earth as a system in and of itself. And so I consider myself an Earth system scientist rather than a biological oceanographer, but I got stuck with what I did my PhD on. And this is it. This is our ecosystem. It's not a closed system. We get materials from space. We also get energy from space. But the thing is, the materials we get from space, we don't need to survive. Life doesn't need it to survive. We need the energy, but unfortunately, we can't use it in the form that comes to us. Only plants are in a position to do that and to make it available to us. So basically, what this picture shows us, and it was taken some time before the previous speaker did his thing. This is a picture from 1972. We began to get these pictures in the late 1960s, thanks to the Apollo missions. We've all seen this picture because I've been told it's the most downloaded picture from the net. But even though you've seen it before, I'm willing to bet you've never laid awake at night and worried about what it's showing you. What is it showing you? Well, first of all, it reminds us that our ancestors made a terrible, terrible mistake when they called this planet Earth. It should be called ocean. But the other thing it's showing you is there's no umbilical cord. No, of course there's no umbilical cord, but what does that mean? It means that once we've used the resources on this planet, and make no mistake, it's not money that makes us rich. We can't eat money. We can't put money on to stay warm. We can't live in money to protect ourselves. The Earth's resources are our true currency. Our ancestors understood this, and they bought and sold from each other with naturalia. And then somebody got smart and said, oh, she might not need bread right now. We'll give her this, and she can trade it for bread when she needs it. And the this was, of course, money. And for a very long time, we had a gold standard related to our money to remind us that it actually came from the Earth's resource. Now we've abolished that. No need for that rubbish any longer. But we can't get away from the fact that our real currency is the Earth's resources. And once we've used them, we're not going to get any more. And the other thing about this missing umbilical cord, is that we can't really get rid of our waste. Climate change is really just a waste problem. We thought that greenhouse gas was gone, and it's not. As a biological oceanographer trained in ocean science, I'm disgusted by the discourse we have in society today about plastic in the ocean. We've been throwing out plastic since the 1950s, knowing full well that it's essentially non-degradable in nature. We've had this picture since 1972 that shows us, doesn't have anywhere to go. It's going to stay on the planet, and 71% of the Earth's surface is ocean. Come on, where did we think the plastic was going to end up? This isn't rocket science. How could it take over 50 years to wake up to the fact that the plastic was in the ocean? And right now, when we think globally, we think climate, 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 climate. It's all about climate change. And a lot of people put climate and sustainability, put an equal sign between the two. But there's nothing very special about having a climate. Every planet or every celestial body in this solar system has a climate. It's just a question of the energy balance. How much heat do you get from the sun? How much of it is stored near the surface of the Earth? How does it move around? What does it come into contact with? And so on. So having a climate or an energy budget, or having elements, things that are left over from the Big Bang, that's not very special either. Every planet has that too. In fact, some people say that Neil Armstrong's footprint can still be seen on the moon for very good reasons. I don't know if that's true or not. But I do know that if we had a footprint on the Earth from 1989, it would be long gone. And why is that? Because there's life, and it's life that makes our planet unique. We don't know what life is, but we know what it does. What does it do? It transforms and it transports those non-living elements on this planet. And every time it's gotten enough, you get enough free energy out of such a transformation that an organism, to support life, that an organism or an organism group has gone in to do that transformation. And for billions of years, we don't know exactly when life evolved, but for over 3 billion years now, it's been the interaction between life and the geosphere, which is the energy budget or climate, plus the non-living elements. This interaction between the biosphere and the geosphere that's created the conditions on Earth. And every time something major happened in either the geosphere or the biosphere, Earth conditions changed. Photosynthesis, boy, did that make a difference. Oxygen in the atmosphere, the ability to have an ozone layer that meant that we all could come up on dry land and not be fried by the UV rays of the sun. Green plants, that you suddenly could take CO2 out of the atmosphere and store carbon in plant material. Or the geosphere, tectonic plates moving around, changing of, or a meteor that hit the Earth 63 million years ago and did it out with the dinosaurs. So major changes within either of these spheres can change the conditions on Earth. But everything being equal, the processes in the geosphere are very slow, and the ones in the biosphere are very fast. But these two spheres come into a kind of quasi-equilibrium. And it's in these periods of quasi-equilibrium, the conditions on Earth are very, very stable. Now, the fact that it's the interaction between the biosphere and the geosphere that create the conditions on Earth, and note I say biosphere, not biodiversity, because biodiversity is all about how many genes, how many species, how many ecosystems. And we don't even know if there's a mechanistic relationship between numbers of genes, species, organisms, and the function of life. So we talk about the biosphere, which is both its diversity, which is important to give it its resilience, because life has had to survive and do its thing and function under lots of different climate conditions in the history of the Earth. And so biodiversity, the function, when we say biosphere, it includes biodiversity and it includes function. And the fact that it's been the interaction between the biosphere and the geosphere that creates the conditions on Earth, of course means that the biodiversity crisis is at least as important as the climate crisis, and it worries me more. It worries me more because when we get control over our emissions, and I say when because we actually do have the technologies that we need today. We haven't made it pay in our economic system, but we could do it today if we wanted to. And when we do, it'll take thousands of years, but the energy balance of the Earth will go back to one that doesn't have a human fingerprint. You won't be able to see we've been here. But every time we lose a species, it's gone forever. You can never go back to a biosphere that doesn't have the imprint of human activities. Now, in the last 50, maybe 150 years, a third force has come into play that can change the conditions on Earth. And that's, of course, us, the anthroposphere. And this is what the Anthropocene, you all heard of Anthropocene, and you all read in the paper last week that the geologists in all their wisdom have decided that there is no such thing as the Anthropocene. We don't need to change the name of the time we're living in. Doesn't matter. It doesn't matter, because Anthropocene is really just our recognition of the fact that we have the capacity, we have the power to be able to change the conditions on Earth. And as this increases, we worry about the fact that it could change the conditions on Earth. And that's where the planetary boundaries comes into effect. We say we need to manage our relationship with the planet in such a way that we don't allow our activities we don't knowingly do something that could change the conditions on Earth. As I say, that's where the planetary boundaries come in. Our first paper was in 2009, our second one in 2015. We learned yesterday that of the non-economic scientific papers, of the 10 top cited in policy documents, both of these papers are among the 10 top on that list. We came with a third update that I was the lead author on for six months ago, on the 13th of September. That paper has now been downloaded 380,000 times. So there's I think, a growing awareness of the need for this discussion in society, especially when you consider that the one we came with in 2015, when we came in September with this new one, the other one had been downloaded 274,000 times. So we're already 100,000 above what the other one made in 8 years. So this is a discussion that I think is becoming more and more relevant and more widespread. The planetary boundaries framework takes as its starting point Earth system science that says the Earth behaves as a complex adaptive system, just like our bodies, just like our families, but it's a larger system. The only thing normative about the planetary boundaries is that we say it would be unwise of humanity to do something that we knowingly do something that could change the conditions of the planet on Earth. Why do we say that? Well, our planet, our ancestors in our current biological form have been on this planet for, somewhere near the first light over there. 200 to 250,000 years we've been here in our current biological form. And there were actually about 10 other humanoid species, but they all went extinct. And ours we were really dead lucky to get through the eye of the needle. We were only about 10,000 or tens of thousands of reproducing individuals left at one point. So there was no biological reason we couldn't have made modern civilizations far before we did. But for 250,000 years, or 200 to 250,000, for all but the last 10,000 to 12,000 of those, we ran around after our food. We had a nomadic existence. Everything that we associate, this is temperature over Greenland for the last 100,000 years, using proxies from ice cores done by some of my colleagues at the University of Copenhagen. And these big jumps that you're seeing in here are about 10 degrees centigrade, happening very, very quickly. So this isn't global, it's over Greenland, but if things are happening over Greenland, they're also happening other places. And so we can see that the Earth has had a really rocky, there have been lots of different states of the Earth in that period when our ancestors have been here. What's interesting is this last period here, what we call the Holocene, and we continue to call the Holocene, in spite of the fact that we're out of the window of variability that's been there for the last 12,000 years. It's this very stable period in which absolutely everything we associate with modern humanity or modern civilization evolved. We're talking Stone Age, Bronze Age, Iron Age, Neolithic Revolution, written language. Everything we associate with modern civilization evolved during this period. So we say, okay, we know for certain that our species can thrive under these conditions. We don't know for certain that we can thrive under others. So it would be unwise. It would be extremely unwise for humanity to do something that could change the conditions on Earth. Now, why has it been very stable in this period? Well, the most important reason is that the Earth's orbit has been unusually circular. But the people who, and you could say, well, I can't do anything about that, and that could change tomorrow, so why should I worry about this? But the people who study the Earth's orbit around the Earth say, no, this will continue for thousands of years to come in the way it is. We don't see any reason to expect this to change unless we change something in the system that could make it change. And so then we go in and say, okay, well, what is it in this complex adaptive system we call the Earth? What is it in this system that maintains it in the way that, in this particular state? And of these important processes, which ones are we impacting? We arrive at the fact that there's 9. And the 2 really most important, the ones in red up there, are biosphere integrity and climate change. We're back to this idea of geosphere and biosphere and their interaction. We call them core boundaries because that's what's been deciding the conditions for the last over 3 billion years. I'm sorry, I have grandchildren. But there are 7 others that we identify that also could be pushed far enough to change the conditions on Earth. Not in themselves, they do it either through the energy balance of the Earth, for example, ozone, the ozone hole, or through the biosphere, for example, felling of forest and so on, or use of fresh water and so on. So we have 7 different activities or 7 different processes in the Earth system that we are impacting greatly. And it doesn't, you don't have to have a higher degree to figure out, oh yeah, we could push every one of those far enough to change the conditions on Earth. Think of ozone, think of pollution, think of ocean acidity. All of these, if you push them far enough, will change the conditions, the state of this ecosystem. Interestingly enough, 3 of these, biosphere integrity, land system change, and our metric there is felling of forest and use of fresh water, are things we take out of the system to survive. All organisms do that. All of the other 6 are about waste. Other organisms don't do that. I was thinking that in the earlier talk about the debris in space. We're very good at leaving waste behind. How has nature survived on this planet, a closed system, we can consider it a closed system in relation to the things that keep life going? How has it survived for over 3 billion years? By not producing waste. Individuals may produce waste, but other organisms have come in to use that waste and bring it back to its original form so the whole process can start all over again. I was actually at a meeting not too long ago where some Americans suggested this waste problem is not a problem because, as was pointed out in the earlier talk, it's getting so cheap to send rockets into space, we'll just take it into space and throw it there. Okay. But 3 have to do with taking things out of the system to survive, and 6 have to do with waste. So this is where we are now. We, in addition to identifying all of these 9 different processes, we try on the basis of understanding the scientific data about how these different things worked under other climate conditions and so on. We try and identify an area, well, if we don't push it out to here, the green is the safe operating space. If we keep ourselves within the safe operating space, there's no real danger that we will change the conditions on Earth. Come outside of this space, and we have increased risks. And when the risks get really high, then the color gets really much darker. So the planetary boundary is placed at the edge of the green area. And many people mistakenly, and some of them intentionally, mistakenly believe that the planetary boundary should represent a tipping point or a threshold. It doesn't. It's like your blood pressure. If your blood pressure is over 120 over 80, it's no guarantee you're going to have a heart attack or a stroke, but it increases the risk. And that's why we try and put it down. And if you were going to use the planetary boundaries as a tool for guiding society on managing its relationship with the planet as a whole, then putting the boundary right there where you think it's going to totally collapse would be very unwise, because societies don't actually, but there's a lot of wiggle room about when we have right now a guardrail that says 1.5 to 2 degrees, and the question is whether or not we're gonna keep that. So this is what we found. 6 out of 9 boundaries are on the wrong side. That was the title of the paper, as you saw. I'm sorry we used that, because the fact that we're on the wrong side doesn't worry me very much, in the sense that in the 1990s, we were either on the wrong side or right on the edge of the planetary boundary for the stratospheric depletion of the ozone layer. Thanks to international negotiation and concerted effort, we've brought ourselves safely back into the safe operating space. So being on the wrong side in itself is not a recipe for disaster. What scares me is that in our 2015 paper, we found 4 of the boundaries were transgressed. We didn't have metrics for all the boundaries in 2015. We found 4 were transgressed. All 4 of those today are more transgressed than they were in 2015, which says that as we stand here, looking at each other, the pressure on these axes in this spider diagram are increasing. And as I say, it doesn't take a higher degree to realize you can go too far on all of them. So you can discuss with me until the cows come home whether we've placed the planetary boundary the right place or not. But the fact that there must be some kind of a limit for how far we can push these 9 parameters is obvious. So what's really new here in this new version? Well, first of all, as I say, all boundaries are defined. We made considerable changes to the freshwater boundary, and this is interesting because there is not a fast team of scientists behind, or one laboratory or whatever, behind the planetary boundaries. We threw it out in 2009 as a kind of like throwing out the gauntlet to the scientific community and saying, hey, if we're going to have to, our ancestors realized, they started out when they stopped that nomadic existence. They started out by taking anything they thought they needed from nature and dropping their waste wherever it was produced. But then they realized, hey, we're getting sick from polluted water that's polluted from our own waste. We're running out of game. We're going to have to make some rules here. You can't defecate there, you have to do it over there. You can't take more animals than you need. You have to use the whole animal, you have to share, blah, blah. So they never solved that problem. We're still managing our relationship with the environment at the local level. When we got to be more people, we said, okay, local's not enough. We need to do regional as well. And if we want clean air and water in Denmark, where I come from, we can't let you guys in the Poles and the Swedes, or the Germans, throw all their waste into the air and water either. So that was regional, and now the biodiversity and the climate crises are telling us that we need to manage at the global level. So we threw this out saying, we need something, here's a good start, or here's what we think is a good start, what do you think? And there's been dialogue backwards and forwards. There have been lots. I think that the planetary boundaries have been cited over 1,500 times in the scientific literature, and different scientists have come in and tried to say, well, we think, have criticized different things. And really, around the freshwater boundary, they were right, the people that criticized, because we only had a blue water boundary. How much are you taking out of flowing water or groundwater? When in fact, we also need a green water, one that has to do with how much moisture we're taking out of the soils themselves. So the freshwater boundary has been changed. But most importantly, I think, is this one up here that has to do with the function of the biosphere. Life, biosphere, all living organisms. We started in 2009 with just one metric, and that was the classic extinctions. How many extinctions, the rate of extinctions. That's the genetic diversity. And as I said, the genetic diversity is exceedingly important because it's what gives the biosphere its resilience when it comes to changing external conditions. In 2015, we realized we needed also a functional metric. We tried something then that didn't really work, and so this time we've changed approach and said, okay, if what life does is move around elements, let's think about this thermodynamically. Carbon is a really important element because it's the backbone of life, and it's also what we're doing to the climate is through the carbon cycling, the global carbon cycling. So let's have a look at carbon and the relationship with biology. And that's, of course, the most important is that biology, photosynthesis, makes it available for all life, makes energy available for all life on Earth. So we went in and did a modeling exercise and said how much photosynthesis was happening on Earth every year in the 10,000 years before the Industrial Revolution. Turns out it was exceedingly stable. Well, of course it was. The conditions on Earth were very, very stable. It also turns out that we humans are removing, appropriating, usurping, whatever you want to call it, about a third of that energy. So HANPP is human appropriation of net primary production. We say now taking away a third of the energy that nature had available to it is clearly too much because look what's happening to biodiversity. This is a driver of biodiversity loss. And you will very rightly say to me, but because of the extra CO2 in the atmosphere, there is a fertilization effect, which means there's more photosynthesis today than there was before the Industrial Revolution. Absolutely true. But that increased photosynthesis is a resilience effect. It's buffering climate change. It's making it that we're not suffering as much from climate change as we ought to be. We can't harvest that. It's protecting us against climate change. So we go back and say we should not be using a third of the energy that nature had available to itself before the Industrial Revolution. We're using too much today. We need to use less. And how is it that we're using it? Well, this is a schematic that explains it, that here you would have the net primary production on the left-hand side before the Industrial Revolution. Now you can see in the dark green in the middle, that's what it is today. But we put infrastructure here. There's no photosynthesis happening on this square meter where I'm standing today, where there would have been before. And we also, through production forest and through agriculture, we take away, we focus the photosynthesis happening there on humans and human use rather than nature's use. So when you put all that together, we're actually taking, there's only about 2/3 of the energy left for nature that there was before the Industrial Revolution. We also, in this study, arrive at the conclusion that we are unlikely to meet the goals of the Paris Agreement unless we stop deforestation. We did this very simply because we went in and said, okay, at different levels of CO2 in the atmosphere, 350, 450, 550, and different levels of felling of forest, the green being in the safe operating space, that's 85% of tropical and boreal forest remaining and 50% of temperate. And then there's the upper end of the increasing risk zone, that would be 60, 30, 60, and beyond in the high, it would be 40, 20, 40. If we had managed to keep our, and this is the green, we're looking at I think it's this one here. If we had managed to keep forests where they were in 1988, then at 350 we would have a slight source from CO2, but of course we're far from 350 now. We're on our way to 450. And there you can see we'd have this lovely sink over here. There are two balls there because politically we only look at 2100, but the biosphere and the geosphere aren't in equilibrium at 2100. So we do it both in 2100 for the politicians and also when they come into equilibrium in 2770 in our models. And you can see that you'd have this nice sink of carbon that we don't have anymore because we felled the forest. And you can see that if we continue our deforestation, as we're doing now, then we'll have this huge source, 200 gigatons of carbon at 450. It'll be less when you get to It'll be less when we get to the 550 because of the increased fertilization effect. But it's source over here. But if we had managed to keep, as I say, to keep our forest from being felled, then we would have a nice sink here by 2100. We did exactly the same thing in the ocean. This seems very complicated. Don't worry. There are two important messages that I will bring you. But again, you can see 350, 450, 550. The first important message is over here. And it says CO2 is increasing in the surface of the ocean. Well, yes, of course it is. The more you increase the CO2 in the atmosphere, the ocean and the atmosphere are trying to get into equilibrium. And so we've got this wonderful big fat arrow going from the atmosphere to the ocean, helping us against climate change. So far, so good. But it's not just, not the only reason why CO2 is increasing in the surface of the ocean. The other reason is that bacteria are more active in a warmer ocean, so there'll be more breakdown of what's going on, of the organic material in the surface layers of the ocean. So you're increasing CO2 in the ocean. No brainer. But we don't talk about that very much when we talk about sucking CO2 out of the atmosphere. There's this underlying assumption if we just take it out of the atmosphere, that'll be good enough. But it won't. Once we get the concentration of CO2 in the atmosphere to be lower than the CO2 in the surface of the ocean, then we're going to have to be sucking it not only out of the atmosphere, but also out of the surface of the ocean. So these overshoot scenarios, we have to remember when we talk overshoot scenarios, there's a tremendous amount of CO2 we're going to have to take out of the atmosphere. The other really interesting point on this table is these two columns here. And essentially what we say is that probably the largest biome on Earth is the one right under the lit area in the ocean. We call it the mesopelagic, and whales go down to do their thing there, and there's lots of... You can't do photosynthesis down there because there's no light. So all of their food is coming from above. It's stuff that's dribbling down to them. And if you use the kinds of models that are used for the IPCC, the CMIP6 models, if you use them to estimate what will happen to the amount of material, I don't think I can point with this, but it's the left hand inside the yellow ball there. Those models say not much difference, maybe a 3% decrease in the amount of material falling down. But if you use empirical relationships that are established by going out and taking a measurement in the ocean here where it's this warm, and here where it's that warm, and over there where it's another warm, and make these relationships, and then try and estimate how much material will be sinking down to this huge biome, we arrive at the conclusion that they may be losing 10% of the food coming in. That's a lot. And paleo evidence suggests that that's happened before. And the mesopelagic is not an area that we usually talk about when we talk about ecosystem effects on nature or climate change effects on ecosystems or nature. But the most important message about this discrepancy here is that the models we're using to make predictions about the future and what the conditions on Earth will be like in the future don't actually capture very well the interaction between the geosphere and the biosphere. Typically in physics, we have assumed physics decides everything and biology rides on the back of physics. That's simply not true when it comes to the Earth system. And we don't have, in fact, if you look at the models that the IPCC is using to predict primary production in the ocean in response to climate change, they don't even agree on the direction of change, whether there will be an increase or a decrease. And if anything has been important for climate evolution on this planet in its history, it's been photosynthesis in the ocean. And the models we're using do not even agree as to the direction of change. And the intermodel difference is greater than the inter-scenario difference that we have in the IPCC. So what are the take-home messages from all of this? Well, first of all, pressure on these critical Earth system processes is increasing as we speak. There's a lot of talk about what we're doing, but pressure on them all, with the exception of the ozone, the breakdown of the ozone hole. And to be perfectly honest, I don't think we're going to get on the wrong side for the aerosols in the atmosphere either, but not because we're concerned about the global effects, but because we recognize that air pollution is bad for us. So I think our concern about our own health will keep us from crossing the boundary on the aerosols. But they also have a huge planetary effect as well. There we use as a metric the change in optical depth in the relative difference between the optical depth in the northern and southern hemisphere. Because if you change that too much, you don't get monsoons where you usually get monsoons and things like that. Message number 2, it's not enough to focus on climate alone. We also need desperately to be including biodiversity. I recently heard an editor of a Danish newspaper say, climate change is a matter of life and death. Biodiversity is a matter of aesthetics. Nothing could be further from the truth. I have artists on my research projects, and I'd had a cruise in 21 where I had my artist with me, and she performed a poem for us. And I can't tell you what that poem was about, but it hit me just because what she'd done was she started using all the letters of the alphabet. And as time went on, she took away letters and made herself just use words that had only the remaining letters. And in the beginning, everything was completely understandable, less flowery language, but completely understandable. As time went on, it got harder and harder to understand. And when she finished, it was just noises and grunts left. And she looked up and said, "Those were species that disappeared." Oh, yeah. When I was a child, they still hadn't figured out how to read the Egyptian hieroglyphics. They could recognize some of the individual signs, and maybe they could put a word together, but they couldn't read the language. And we've been focusing so much in biodiversity on identifying the letters that we don't know the language and we don't understand how physics and biology talk together. That's what my research is all about right now. I'm taking cores from both ocean and land off Iceland and analyzing them for eDNA in order to be able to go back and say, what did nature look like in various climate configurations. We're already using too much biomass. We need biomass. We need the products of photosynthesis, but so does nature. We're not as smart as plants. We can't do photosynthesis, but we're smart enough to be able to help plants do photosynthesis places where they don't usually do it. Bioreactors on the roofs of buildings, at the surface of the ocean. The ocean covers 71% of the Earth's surface, and it gets light, just as much light as comes onto land. We need to work for systemic governance and institutionalize, maybe not the planetary boundaries framework itself, but something that does. We can't continue to deal with climate in that corner with one convention and biodiversity in that corner with another and pollution up in that corner. Well, those corners with several different conventions that we have. We have to bring these impacts together into a systemic understanding. And we need support for we need to support decision-making tools that better capture the interactions between the biosphere and the geosphere. In other words, true Earth system models, not just the GCMs we're working on at the moment, which, as I say, take the starting point that it's all about physics, and then biology will ride on its back. Nature actually tells us what will happen if we don't begin to manage our relationship with the planet as a whole, if we don't respect that there are certain biophysical limits to how much we can impact the planet. I suspect many, probably all of you, or possibly all of you, at some point in your educational career have been in a laboratory or been given a bottle that's got some nutrients, some media in it, and you were asked to put in some kind of a microorganism, usually one that does photosynthesis because it has color and then you can see it, and you put it in to see what happens. Well, what happens is, first, you get a lag phase. It grows very, very slowly as it adapts to its environment. And then you get an exponential phase. And then as it starts running out of resources, then it stabilizes. We call that the stationary phase. And at the end of the day, it collapses. It collapses because it gets poisoned by its own waste products. If you look at the human population, we had our lag phase. We've had our exponential phase. We're going into our stationary phase. The question is how we avoid a phase in which the whole thing collapses. The important thing here is that ecosystems, this doesn't happen in ecosystems. Organisms persist, their numbers go up and down, but organisms persist generally in ecosystems until an organism comes along that does the function that the first one did better, and then the first one goes extinct. But generally, it takes a long time before organisms go extinct. And when they do, another organism is there to take on the role that they had in the system. And organisms this doesn't happen in ecosystems because ecosystems are sustainable circular economies. They don't produce waste. They don't deal with a closed, they use everything within the closed system that they're a part of. If you consider the Earth as a closed system, they recycle everything within that system. So we talk all the time about nature-based solutions. The ultimate nature-based solution is, of course, that we focus on our use and throw out culture. And again, it was really interesting hearing the talk before mine here about debris. And some people are saying, well, you can't throw any junk out 50 meters. I mean, wait a minute. Who says we own that and can make those kinds of decisions? We had a paper in the Proceedings of the National Academy of Sciences here in January where we argue that the global commons concept is outdated, where you had things like global commons for the Antarctic or the open ocean, because basically what the global commons concept is that who's going to get the rights to use the resources in places that aren't under national jurisdiction. And we've proposed the idea of having a planetary commons, things that we must protect, processes and processes within our ecosystem that are necessary to maintain the conditions of that ecosystem and that must be protected by our society as a whole. Now, of course, this isn't easy because we don't have and we don't want a global governance. On the other hand, we have a global economy and we manage somehow to manage that. So I'm sure we can if we will, but we have to recognize the fact and respect the fact that we are part of a system. We are not above nature, we are a part of nature. And in a closed system such as the one that we're in, there are no such things. Nothing is external to it, so there are no such things as externalities, and we need to approach our economic models with that idea. Thank you.